First of all, good afternoon. I hope you had sufficient amount of lunch, but not too much, so that you don't sleep. So the talk of today is real-time recommendations. I'm going to talk of a particular type of recommendation which can be put into production fairly easily. There are fairly many varieties of recommendation engines that are available, but this is going to be real time. The applications could be very many, including news. So if you are subscribing to the BBC and if you are looking at certain news, certain other news should pop up, or advertisement related to that news should pop up. Given such scenarios, there are, in typical world case scenario, what we have is basically a recommendation engine which works offline, meaning it updates itself in the night, 1 o'clock, and then does the recommendation in the morning whenever the users come to your website. But if you go in news channel, advertisement industry, so many other industries, they want real-time recommendations, not something that you go in 1 o'clock in the night, recreate your algorithm, and come back and come up with the recommendations. So in such scenarios, what is necessary is to have that updation process pretty fast. Let me just come to the agenda here. So basically, what I'm going to speak of the background of the real time, which I did a bit. Then what would be the speed tricks that are required to make it real time, accuracy tricks also, and then basically how it gonna go in moving into real time. So puppies and ponies. Why puppies and ponies? It's basically a itemization of the items in real world. So I say them puppies and ponies. Every industry has their own sorts of items. If you go to Netflix, you have movies as your items. If you go to some news channel, newsroom, so many, so on and so forth, you have multiple items. And there are users which are subscribing to these items. So in this case, what we have is actually three matrices. One is called history matrix, another is called co-occurrence matrix, and third is called indicator matrix. So history matrix is what we have from our log files. The rows are basically the users and columns are basically the items, in this case puppies and ponies, with some other items as well. So what we do is basically we convert history matrix to co-occurrence matrix and then co-occurrence matrix to indicator matrix and use this indicator matrix as a recommendation to the user for an item. So how do we go about from first step, that is history matrix to co-occurrence matrix? It's basically pretty simple. The first matrix that you see here is a user to item, but the second matrix that you see is a item to item. That's what we call in a recommendation engine framework. So how do we create user to item to item to item? That's pretty, let's call matrix A. How do we convert it? It's fairly simple. A transpose A. That's simple mathematics. But now think, I'm going to switch in between small data and big data here. So just think of big data problem. Multiplication of matrix, transpose of matrix in a big chunk, big data is pretty hard. How we solve it, I'll come to that later. But I'm just putting some thoughts, putting some questions in your head. How do we go about millions of rows and millions of columns? In this case, probably just 4 rows and 4 columns, but that's still a big data because it's a big screen compared to compared to this, but nonetheless. So coming to next step, that is from item to item matrix to indicator matrix. How do we solve this? This is in real world or in data science domain, what we call is sparsifying the matrix. So we have this A transpose A, but what we do is we sparsify A transpose A to make it binarize. In your co-occurrence matrix, it's not binary, it's integers. But in co-occurrence matrix, in indicator matrix, we make it binary. How do we do? Again, sparsify. How do we do sparsify? One of the methods is log likelihood ratio. Simple method, but works. So each row in indicator matrix becomes a field of search engine. Now what I am doing is I'm going to exploit search engine. I'm not going to use the typical recommendation engine sort of stuff. I'm going to use search engine. How am I going to use it? How am I going to exploit it? How am I going to abuse it? The search engine technologies that we have. We have Lucene, we have Elasticsearch, we have so many things. We can use any of them depending on the application, depending on what you like. So let's coming back to the recommendation. What we see from the history is Alice likes apple and puppies. Charles likes bicycles. Bob likes apple. Now the question is, what else would Bob like? Now given our history matrix, given our co-occurrence matrix, it is fairly simple to answer: a puppy. Because it's a one-to-one. Whenever somebody likes apple, there was a co-occurrence with puppy. So it's fairly simple. So if I have to say that basically Bob also wants a pony, now what would happen? Now consider that everybody in our data, or every user would like to have a pony. What implications would that be? So in terms of recommendation, so let's consider everybody has a pony. Amelia is also a person, also a user, and the first thing that she chose as an item is a pony. So what would you recommend to Amelia? Because everybody has pony there. So it's a generalization. So it's everybody. What would you say to that? So the question is basically, there is nothing basically to predict. There is nothing basically to recommend, because everybody has it. It's a common across all the users. So you can actually recommend anything because it comes with everything. So the problem of raw co-occurrences is we have three problems here. Very popular items co-occur with everything. Very widespread occurrences is not interesting to generate the indicator for the recommendation. So indicator matrix that I discussed earlier. What we want is basically anomalous co-occurrences. Those anomalous co-occurrences are kind of interesting, and that we can go for recommendation. So to get basically useful indicators from the behaviors, what we use is we use log files to build the history matrix, transform that log files, as I discussed earlier, to co-occurrence matrix, which is item to item matrix. The third step is look for useful indicators, meaning anomalous indicators. One of the technique that I said earlier is log likelihood ratio, which in Mahout was item similarity job. It can be found similar cases with other open source things. Now let's look at 4 cases here. There are item A and item B. I'm just going to work with binary fashion here, so only 2 items. So let's consider the topmost, leftmost case where when item B was present, item A had 13 times occurred, only 13 times, but not B and A was like 1,000 times, which in reality means the co-occurrence or percentage wise it's 1.3 only. If you go bottom, it's 100% when item A and B occurred together is 100%. The third case is top right, which is also 100%, but in this case it's not a big data. It's very small. So you wouldn't be able to say that this is a kind of a good indicator for referencing or for recommendation purpose. The last one, right bottom, seems to be a good, which is basically I just multiplied by 10 from the left, but still a good thing because there is a nearly 100% when A occurred and B occurred, but not A and not B is also tenfold, which is like 100,000. So what happens if I use LLR? So if we look at it, it comes to this. So if I use LLR, our root of log likelihood. It boils down to first matrix is 0.9, which is like one standard deviation. We go further, second matrix is 1.95, third one is 4.52. If you are a physicist who is looking for particle physics and finding a co-occurrence, probably the third matrix is good for you. So your threshold should be more than 4.5. But in recommendation system, what we want is really anomalous data. Anomalous meaning very few occurring or long tail data in this case, where you have co-occurrences, but they are not so common. And that's why when we say real time, we go for such kind of occurrences with LLR. So we have threshold, we can set threshold above 10, above 15, depending on the size of data that you have. So that's kind of my choice that I will go for if I have to recommend something. So coming to the setup of recommendation hinges. So it's gonna be, I have this item metadata to begin with. I ingest via NFS to my search engine. What document look like? So there is a puppy document which has an ID, which has a title puppy. Probably you can have a description of it as well. The sweetest little puppy or whatever, my dear puppy. Keyword could be puppy, dog, blah, blah, blah. Now the next point is from our co-occurrence matrix, what we see is whenever somebody has like puppy, they also have like the apple. So what we go, we write an indicator, and that is my apple is there, so T1. We can have more indicators there depending on the item to item matrix there. So how do we create this matrix? Basically, it's a co-occurrence mechanism. If you look at it, it's basically a simple self-join, meaning in this case, addition of the occurrences. It's fairly simple. It's nothing complicated here. No big complicated mathematics that you are doing. Still, it works. So what we are doing is simply adding self-joining. What we are missing, or what generally tends to we forget, is we also have to think of cross co-occurrence mechanism. Let me explain why. If you go to Amazon website, or if you have your own music website or some website, or hotel reviews, hotels website, you tend to, if you before choosing, let's say, a hotel, you tend to go below, see the reviews, what has been written about the movie, about hotel, about any item in this case. And if the reviews are great, or restaurants in this case as well, if the reviews are great for that restaurant, you tend to go to that restaurant. So in this case, what you are doing, it's not only item, but you are also doing certain actions, which is like scrolling down. That's also one action that you can have inbuilt in your recommendation engine. So what is that? Those actions we can define, and that I will call, let's say, a B matrix. So I'm joining A and B and finding again the co-occurrences, or in this case cross co-occurrences. But with this, I'm only going to use the first row. The second row is pretty much of no use in this. So I have done a simple co-occurrence based recommendation engine, if I may say so, at this point of time. So what I have done is with also certain actions involved in it. So if it just simply how many co-occurrences there are, I will threshold based on root of LLR, and that's it. Now, this is fairly simple, but how do we make it scalable? How do we make it real time? That's the question. So let's have a word about scaling of this phenomena. So what I mean by scaling is there are some, if we have matrix which has millions of items, the co-occurrence matrix would be million rows by million rows, which is fairly big enough. And if you have to work on it, it's again going to be fairly computationally costly. So what you do is you downsample. You downsample in the length, you downsample in the limit of maximum viewers. What we call is interaction cut and frequency limit. What has been seen is even if you downsample randomly, if you downsample most recent, or if you downsample certain by number, fixing the number, let's say common limit is 300 or common limit is 500. With these downsampling, in both cases, the results have not been impacted. This is one practical implication of downsampling, which is positive. So you don't have to work on millions of rows. You have to downsample it. So that would help in parallelization. In actually, you can work with this even on a single machine. Yeah.
One question is downsampling to 300 items. Is this on 300 items per user?
Yeah. So there is a paper you can also read if you want. So let me tell you about what it means in terms of computation. So number of pairs, if we think of for a user history, it becomes, if there are k distinct items, it becomes k squared by 2. That's a pair. Oh, it's already 20 minutes. Awesome. So, so if we downsample, what happens is, so if you don't downsample, it's quadratic. If you downsample, it becomes fairly linear. Certain results. Batch scaling, again, a possibility. Particularly frequency sampling, max co-occurrence count is small. I mean, these are pretty much positive sides for making it real time and making it productionizable, I would say. Impact on interaction cut on downsampling, this is kind of intriguing. The reason is amortization cost is low. Incremental matrix factorization is hard, everybody knows that. Scaling matters most at scale. That's everybody also knows it. Coming to online updating, what is sorry, I'm a bit crunched with time. So requirement on online algorithm is each unit input in this case is basically must require O1 work, and that's the theoretical bound. The constants have to be small enough on average. Basically, this is a pragmatic constant. And total accumulated data must be small as well. So again, a pragmatic constant. So what happens is this is my framework for online updating or real-time recommendation. What I have to do is basically want this batch co-occurrence to be real-time actually. So this is an updation process. How do I do it? Because basically user histories are pruned. Only a limited number of values updates need to be incorporated. This bound is just twice the interaction cut that we have, Kmax. Bounding the numbers of updates trivially bounds the time as well. So coming to maths, okay, it's bit. So Eij is basically the difference that we are talking about. That's the updation. So this is simple mathematics. What happens is with interaction of k bounds, this boils down to O1, and that's fairly makes it easily updatable, easily computable, and scalable. So, but does it get better? The new so the question is, does it get better? So the new observations may be pruned. For users at the interaction cut, we can ignore updates. Similar for frequency cut, we can ignore, updates meaning all the updates. So at million songs data size, half of all updates are pruned. So on average, Ki is much less than the interaction cut. LLR cutoff, as I spoke, avoids almost all updates to index, and this helps average grows slowly with frequency cut. Again, certain good graph, but let's skip this graph. So let me recap. I think I'm running out of time. Co-occurrence based recommendations are very, very simple. Deploying with a search engine is even better. It helps. in terms of productization, in terms of real-time application. So similar effect occurs in online form of updates. Only dozens of updates per transaction needed. It's not everything. Data structures required is relatively small. Given we are using the open source community, it's fairly simple. There's nothing that you are doing on your own. We are using what is there. Finally, online recommendation is very feasible and almost easy. So there is a book from one of our chief architect, and that is Ted Dunning, and that's all about ponies. So if you want, it can be downloaded from our website as well. Yeah, so any questions?
I saw a lot of you taking notes, so I think he did a great job of presenting and talking about ponies. Let's give it up for Onkar.
Thank you.